Hello, good day I bid to everyone. I am Aina from Group 15. Me, together with my dearest groupmates, Aimal Aqilah, Najwa Majid, Sara, Anisah and also Whitney, will present our design for Group 3 base oil production plant. Before we proceed further, this is the overview of our presentation today. The timestamp for each parts are also displayed so it will be easier for you to move between sections. Alright, so to give a quick recap, prior to designing our production plant, several alternatives have been developed and compared, to which includes hydroprocessing unit, hydroprocessing routes, and also solvent refining routes, and also the combination of both. After comparing, we have chose hydroprocessing route, alternative 1, because it is more friendly, environmental friendly, and also it can produce high purity base oil. So with that being said, our plant mainly consists of 3 reactors, namely hydrocracker, hydroreactor, and also hydrofinishing. Alright, so after a thorough design process and after we have simulated this process in Aspen HYSYS, we draw our process flow diagram in Visio. So as can be seen here, this is our PFD before heat integration, in which the unit highlighted in green is our reactors, while unit highlighted in orange is our separator. Our separators are distillation column, high and low pressure separator, and also gas separator, which are installed to recover hydrogen gas and also to recover light gas. So next is PFD after heat integration. Heat integration was done in hydrocracking unit and also in hydrodewaxing unit. So after heat integration, utility consumption has been managed to reduce as much as 36% in unit 100 and also reduced by 29% in unit 200. Okay, so proceed to our control strategy. There are several control strategies that have been implemented widely in our plant. However, in this recap, only 3 will be highlighted. First, in our unit 100, where we implemented cascade control at our distillation column. Second is feedback controller implemented in unit 200 in order to control the reactor temperature. Last but not least is feed-forward controller implemented in unit 300 to control the pressure inside C301, which is our gas separator. With that, a piping and instrumentation diagram has been drawn using Microsoft Visio according to the process control strategy implemented. So moving forward, this is a sample of our complete HAZOP that have been carried out for node 1, 2, and 3. So the parameters of HAZOP which apply to our plant design intended are temperature, flow, pressure, and also level. So the first node is at hydrocracker R101. Second node at heat exchanger E101. And the third and last node is at the whole distillation column C101 network. Lastly, after considering the required buildings for our plant, a plant layout has been drawn using Adobe Illustrator. Our plant is located in Sungai Udang, Melaka. So that is all for PDP I Recap. Thank you.
For facilities that stores, releases, transports, treats, or disposes of scheduled waste are subjected to the following regulations, which are environmental clean air regulation, environmental quality scheduled waste regulation, environmental quality sewage, and industrial effluent regulation. So based on our waste, which is alumina, it is alumina and zeolite are under waste catalyst, while cobalt molybdenum is under sludges containing one or several metals. And for other waste, it is categorized under acidic sludge. because it contains ammonia and several other chemicals that are acidic. That's all for me. Thank you.
For the solid treatment part, since the hydroprocessing route is operated with the presence of catalyst and catalysis plays an important role in each of the catalytic reactor, there are two types of catalysts that are being used, which are the nickel molybdenum sulfides supported on alumina and the platinum supported on ZSM22. This catalyst, solid catalyst, contains the metals, oxides or sulfides, which will become solid waste after use. With respect to this method, the disposal of spent hydroprocessing catalysts requires compliance with stringent environmental regulations because of their hazardous nature and toxic chemicals content. The appropriate treatment strategies for the spent catalysts are listed as follows, which the first one is the regeneration and reuse of spent catalysts, cascading reuse spent catalysts to other process units, and the last one, the recycling spent catalysts as the raw materials. For the regenerating and reusing the spent catalyst, it can reduce the spent catalyst waste generation as well as catalyst replacement costs. Off-site regeneration of hydrotreating catalysts resulted in better activity recovery due to the close control of regeneration temperature, better evaluation of reusability by a variety of characterization for catalysts, as well as the quality control test. For the cascading reuse spent catalyst, the spent catalyst discarded from the high severity hydrotreating processes in other less severity or less demanding operations is one of the appropriate treatment strategies. It is possible to shift the catalyst from back end reactors, which are deactivated to the lesser extent by metal deposits in front end reactor. Okay, according to the previous studies, such cascading of spent catalyst helps to maximize the value of catalyst by allowing them to generate revenue from the spent catalyst by reducing disposal costs and reduce the cost of the next catalyst load. In this case, okay, for the last appropriate strategies, the recycling spent catalyst as the raw materials. In this case, the spent catalyst of fluid catalytic cracking (FCC) is used in the cement and concrete production. In this case, the addition of spent catalyst favorably modified the porous structure of the concrete and able to increase the strength, density, as well as to reduce the water absorption, and thus preferred to be substituted with the cement concrete production. That's all from my part. Thank you.
Hello, my name is Sara, and now I will continue for the CAPEX. So for the purchase cost equipment PCE, it was calculated from the cost index formula, which can be referred from the chemical engineering plant cost index. And after totaling up all the equipments, the PCE was found to be 46 million ringgit. And next is for the physical plant cost, the fixed capital investment, and also the working capital. So after calculating the PCE, we can then multiply it by the fluid processing factors as shown here in all these three tables. Then we can total up the fixed capital investment and working capital to get the total capital investment, which is 375 million ringgit. And next is for the project economic evaluation. So for the project economic evaluation, here are some of the assumptions made, where the plant life is of 15 years, and for the construction period is 3 years, and the MARR is 20%. And here is the cumulative cash flow, where at year 15, the CCF is 26 billion ringgit. And next is the payback period. So it was found that the payback period is at year 2. And for the rate of return, it was found to be 70.89%. So this project is considered as worth investing, as the ROR is more than the minimum expected rate. And for the net present worth value, the net present worth is found to be 12 billion ringgit. So because of the net present worth value is positive, then it is considered as economically feasible.
Hi, I'm Whitney. So now I'm going to talk about the operating expenditure, which is OPEX of our plant. The operating expenditure OPEX is an ongoing cost for running a product, business, or a system. So the OPEX consisted of two major contributing aspects, which is the fixed operating cost and variable operating cost. Then, the direct cost can be further divided as the fixed operating cost and variable operating cost. So based on the table, the fixed operating cost of our plant is approximately 68 million ringgit, while the variable operating cost is 3.7 billion ringgit. Apart from that, the indirect operation cost for general expenses in our plant comprises of the administrative cost, distributing and marketing, as well as the research and development, which give a total of 35 million ringgit per year. Therefore, by adding the total direct and indirect operational cost, the OPEX of our plant will be approximately 3.8 billion ringgit per year. Next, I'm going to talk about the gross revenue of our plant. There are a few major components or products that will be produced by our plant. So the base oil is one of the primary components for our production, and the revenue of the base oil in our plant is about 6 billion ringgit per year. While there are other components too that are produced in our plant, such as naphtha, which will make around 198 million ringgit from it, while kerosene with a revenue of 672,000 ringgit, and diesel with a revenue of 4 million ringgit per year. Hence, our plant will get a gross revenue of approximately 2.6 billion by subtracting the total annual revenue with the OPEX. So now I'm going to discuss about the economic potential evaluation of our plant. So the economic potential evaluation is to provide the estimation of the profit generated by our plant. So the EP1 is obtained by subtracting the total product revenue with the total raw material cost, and we can obtain 2.74 billion ringgit per year. As for EP2, before heat integration, the EP1 is subtracted with the total utility cost before heat integration, and we can obtain 2.727 billion ringgit per year. Thus, for EP2 after heat integration, the EP1 is deducted with the total utility cost after heat integration, and we can obtain 2.73 billion ringgit per year. At last, for EP3, the EP2 will be subtracted by the purchased cost of equipment throughout 15 years, and we can obtain 2.73 billion ringgit per year. So now I'm going to talk about the land cost of our plant. The site selection can affect the value of the land and the additional cost. Land prices are not included in fixed capital investment during calculation of the total expenditure, as the value of the land increases over time. So the total area of our proposed plant is around 715,000 square feet, while the price of the land is estimated to be 33 ringgit per square feet, which makes our land of our plant cost around 23 million.
Here is the presentation outline for my presentation. The first one is the design methodology, followed by the sample calculations, specification sheet, mechanical drawing of equipment, and lastly, the cost estimation. The basic flow of the components in the hydrocracking and hydrotreating reactor is shown in the figure displayed. The heated mixture of these three feedstocks enters the top of the reactor, in which will be coming into contact with the H2 quench at each of the intervals between the catalyst bed. The presence of catalyst will promote the reaction between the feedstocks and the H2 by passing through the catalyst beds. The treated feedstocks will be the bottom product of the reactor prior to enter the catalytic hydro-dewaxing unit. As we can see, the inlet and outlet stream of the reactor 101 is obtained from the HYSYS simulation software, which gives the temperature of 400 degrees Celsius and pressure of 7,500 kPa as the inlet, and the outlet will be the 393.35 degrees Celsius with the same pressure of 7,500 kilopascal. The overall design methodology for hydrotreating and hydrocracking catalytic reactor will begin with the selection of type of reactor, determination of optimum operating conditions, calculation for reactor diameter and height, and followed by the mechanical design, and lastly, specification sheets and mechanical drawing is provided. For the basis selection, since the chosen process is heterogeneous process that involving the liquid reactor and solid catalyst, there are two types of heterogeneous catalytic reactor that will be analyzed based on the compatibility towards the process involved. The two are the fixed bed reactor and the fluidized bed reactor, in which they are distinguished by the motion of catalyst particles. As referred to the table provided, the fixed bed reactor with multi-stage of catalyst beds is selected as the most convenient reactor to be used for the lube hydrotreating and hydrocracking process by comparing their advantages and disadvantages. For the hydrocracking catalyst, these catalysts are dual function catalysts, in which the hydrotreating catalyst, mostly nickel and molybdenum, provides the hydrogenation function. Meanwhile, the acid components will provide the hydrocracking components. The process are used interchangeably with respect to the operated catalyst. Hence, in this project, the nickel molybdenum sulfides supported on alumina is selected as the most feasible catalyst for hydrotreating and hydrocracking process due to the high converted product is obtained. For the process design of hydrotreating and hydrocracking catalytic reactor R101, the volume of catalyst bed is calculated by using the liquid hourly space velocity and the bed void fraction. And the total volume of catalyst bed pack with catalyst pellets is obtained is 201.27 meter cube. Meanwhile, from the volume of catalyst bed, we can calculate the total length and diameter of catalyst bed with the ratio of length to height to diameter ratio of 2 to 1 ratio. As we can see, the diameter obtained for the catalyst bed is 4.909 meter, meanwhile the height is 9.82 meter. Based on the height of catalyst bed obtained just now, we can calculate the height of reactor vessel by which a typical reactor having about 10% of free space over the bed to support the catalyst bed. Hence, we can multiply the height of catalyst bed with 1.10, which gives the height of reactor is 10.802 meter. For the diameter of the reactor vessel, as the typical ratio of 2 to 1 of height to diameter ratio, it gives the diameter of reactor vessel of 5.401 meter. For the reactor design pressure and temperature, the maximum allowable working pressure, also defined as the maximum gauge pressure permissible at the top of the completed vessel in its operating condition. The design pressure will be normally in the range between 5% until 10% above the normal operating pressure in order to avoid the faulty during the minor process upsets. Hence, it gives the design pressure of 7,590 kilopascal. As referred to the Petronas Technical Standard (PTS), the design temperature for the reactor shall be taken as 10 degrees Celsius above the maximum operating temperature. With respect to this matter, the operating temperature for the typical hydrotreater the typical design temperature of hydrotreater and hydrocracker process is most preferably to be performed around 410 degrees Celsius. As referred to the Chemical Engineering textbook of Volume 6 in 4th edition, the reactor shell thickness is given by the formula, which gives the calculated shell thickness of 311.6 mm. Meanwhile, the reactor diameter can be obtained from the thickness, which can be calculated, that gives the outer diameter of 6,024.2 mm. For the reactor head end closures, the hemispherical heads is selected as the most preferred heads for hydrocracking and hydrotreating catalytic reactor, since it has the strongest shape and capable of resisting around above 3,000 kilopascal of design pressure. Hence, the thickness gives 150.01 mm, which gives the total height of 11.102 meter. For the bolted flange joints, the welding neck flanges is selected as the preferred flange, since it has the less stress and high strength to withstand the high shear and vibration loads. Meanwhile, the bolt material of 5% chromium molybdenum steel is selected with allowable stress of bolting material around 138 million Newton per millimeter square. The nozzle sizing is obtained from the Chemical Engineering textbook of Volume 6 in 4th edition, which gives the inlet diameter of nozzle around 178.02 mm. Meanwhile, the outer diameter of nozzle of 181.15 mm. The skirt support of reactor vessel is given by the bending stress of 0.138 Newton per millimeter square and the dead weight stress of 3.415 Newton per millimeter square, which comprises of tensile and compressive stress. For the process design and mechanical design that have been calculated, it can be summarized in the specification sheet, which comprises of design code, mechanical data, and the last one is catalyst data. The figure shown is the mechanical drawing of hydrotreating and hydrocracking catalytic reactor of R101, which comprises the total height, reactor height, and the bed catalyst height with the catalyst bed dimension and the hemispherical head dimension. The cost estimation for hydrotreating and hydrocracking catalytic reactor R101 is calculated based on the base index at year 2000 with value of 435.8, which compared with the current index of 594.1 from the year 2020, and the calculation gives the total cost of reactor with around 8,143,643 ringgit Malaysia. That's all from me. Thank you.
Hi, my name is Sara Anisah from Group 15, and I will talk about the major equipment R201 hydroisomerization reactor. So here is the overview of the whole presentation, and next is the general description. So the hydroisomerization reactor will receive hydrocracked oil from furnace F201 and will be sent to hydrofinishing unit. So in the reactor, there will be some hydrogen quenching. And here is the inlet operating conditions, where the temperature is at 360 degrees Celsius, while the pressure is at 7,500 kPa. And similarly for the outlet operating condition as well. And next is the design methodology. So the first method of design is by selecting the type of reactor, then selecting the type of catalyst. The third one is calculating the reactor sizing. The fourth one is doing the mechanical design. The fifth one is doing the specification sheet. And lastly is by doing the technical drawing. So for the type of reactor, packed bed reactor was chosen. The reactor type was compared with three types of continuous flow reactor, which includes the CSDR, PFR, and also the PBR. So the usage were compared, and it was found that the PBR is the most suitable one, as it uses it is used in heterogeneous phase reactions and uses catalyst. And for the type of catalyst, the platinum supported on ZSM22 catalyst is chosen, as it shows high yields of up to 90 weight percentage. And next is the reactor volume. So the reactor volume can be calculated from the volume of the catalyst bed itself. So the catalyst bed volume can be calculated from the space velocity equation. So from here, it was determined that the volume of bed is 150.8 meter cube. So assuming that the ratio of the length to diameter is 2:1 for the volume of bed, the length of bed and the diameter of bed was calculated. Then from here, we can calculate the volume of reactor by assuming that the length of the vessel is the 10% of the length of the vessel is filled with extra fittings. So from there, we can multiply the length of bed with 10% to get the length of the vessel, which is 8.95 meter, and the volume of reactor is calculated and found to be 589.78 meter cube. And next is the pressure drop. So the pressure drop can be calculated from the Ergun equation, and it was found that the pressure drop is 41.79 kPa. The next is for the mechanical design. Starting off with the design operating conditions. For the design pressure, it was assumed that the design pressure is 10% above the operating pressure. So the design pressure is now 8,250 kPa. While for design temperature, it was assumed that design temperature is a minimum of 10 degrees Celsius above the operating temperature. So now the design temperature is at 370 degrees Celsius. For the material selection, the material chosen was stainless steel, and the allowable stress is shown here, which is 16,700 at 300 degrees Celsius, while the shell thickness is also calculated from this correlation, where the thickness of the shell is 154.19 millimeter, while the outer diameter of the reactor is now 4.95 meter. For the reactor head enclosure, the hemispherical head was chosen as it is shown to be suitable for high pressure processes, and the thickness of the reactor head enclosure was calculated, and from there we can calculate the total height of the reactor, where total height of reactor equals to height of head plus height of closure plus height of vessel. So the total height of the reactor is now 13.66 meter. And here is the specification sheet for the reactor, where I include the process data, the catalyst bed, the reactor vessel, the hemispherical head enclosure, and the nozzle. And here is the technical drawing, where I included the side view of the reactor, the hemispherical head, and also the catalyst bed dimensions. And all dimensions are in millimeter, where the scale is for 10 millimeter equals to 1 meter in real life. And that is all from me. Thank you.
Hi, I'm Whitney. So now I'm going to present about one of the major equipment of our plant, which is the hydro finishing reactor. So this is the design methodology of the hydro finishing reactor, which start off by the selection of hydro finishing reactor. Secondly is collecting of operating conditions, inlet and outlet stream data. So the third is reactor sizing and dimensional calculation. Fourth will be the reactor internal sizing and calculations, while the last will be the specifying the mechanical design of reactor. Next, I'm going to talk about the basis of selection and operating condition of the hydro finishing reactor. At first, the type of reactor that is selected of this particular hydro finishing process is the fixed bed reactor with vertical orientation and continuous operations. The advantage of using the fixed bed reactor instead of other types of reactor in the hydro finishing process is that it is able to lower capital and operating cost. Next, it also has lower pressure loss and less possibility of erosion occur inside the reactor. Furthermore, the catalyst that is chosen for the hydro finishing process is the nickel molybdenum catalyst. The nickel molybdenum catalyst is one of the common catalysts used in this process due to its high hydrogenation activity, greater saturation of aromatic rings, and required less severe operating conditions in the reactor. So then for the operating conditions of the hydro finishing reactor, the data was taken from HYSYS simulation. The two streams that will be taken into account are the stream 23, which is the inlet, and it is the hydro dewaxed base oil, and stream 25, which is the outlet, and it is a hydro finished base oil. So now this is a sample calculation of our hydro finishing reactor. There are some of the main sample calculation included, which is the total reactor height. And it was determined by first calculate the height of bed, which is 19.225 meter. Then the height of quenching space in between two of the beds in the hydro finishing reactor is around 3.05 meter. Then the ellipsoidal head will be selected as our reactor head, and the height is 2.52 meters. And therefore, the total reactor height can be obtained by adding the height of bed, quenching space, and reactor head to get 27.32 meters. Next, the reactor internal diameters obtained is 7.69 meters. To calculate the reactor external diameter, the reactor shell thickness will be determined first and get 0.5998 meters. Hence, the reactor external diameter can be obtained with 8.89 meters. And furthermore, the pressure drop of the reactor can be determined by using the Ergun equation. From that, the pressure drop of the hydro finishing reactor is around 260.84 kilopascal. At last, the tube reactor of the reactor is 0.0191 meters square, while the volume of the tube is calculated to be 0.3668 meters square. By dividing both of the value, the number of tube will be obtained, and therefore there are a total of 975 tubes in our hydro finishing reactor. This is the specification sheet of the hydro finishing reactor of our plant. The specification sheet is included the operating data, design code, mechanical design, as well as the vessel weight. For the mechanical data, the material of the reactor shell and head are made of carbon steel. The carbon steel is a commonly used material for reactor and vessels due to its high durability. So the carbon steel is extremely strong and shock resistant, which makes it also a popular choice for construction and piping. And apart from that, the material construction for gaskets, flanges, and nozzles are stainless steel because they are able to withstand high changes of temperature and pressure and provide better mechanical strength to support the reactor. And now this is the mechanical drawing of our hydro finishing reactor. From the diagram, the reactor has two beds, the upper side and the lower side, and it is divided by the quenching space. Then the ellipsoidal type of head is selected for the design for our reactor head because it is more economical than other types of reactor head like toruspherical head and hemispherical head. So apart from that, the external diameter of our tube pitch is also shown, and it's around 0.088 meters, while the internal diameter is around 0.0779 meters.
Hi, I'm Aina, and I will be presenting about design of distillation column C101. The design methodology is to first identify the stream properties from HYSYS, followed by determine operating conditions. Next is to select type of contacting device and also to determine number of stage and reflux requirement. Following that, we need to estimate the column sizing as well as the column internal design and mechanical design. Last but not least is to come up with a technical drawing and also a specification sheet. So moving forward for our distillation column, decision selection has been made for type of column and also type of tray. For type of column, we have compact pack column with tray column, while for type of tray, we have compact sieve tray with bubble cap. So it is decided that we will use tray column and also sieve trays as both are effective at a very low cost. So moving on to the process design, the first criteria is to find the minimum number of stages. To find vapor pressure, Antoine's equation has been used and relative volatility is calculated using this formula. To find the minimum number of stages, Penske's equation has been used as our feed inlet is a multi-component. The resulting minimum number of stages is 6.03 stages. Next, Underwood equation has been used to calculate the minimum reflux ratio. Our Q is 0.211 as our feed is only partially vaporized. The R mean obtained is 0.0052183. Next, from that, we can calculate the actual number of stages and reflux ratio. And we obtain our reflux is 0.007827 when we use reflux ratio of 1.5. And the total number of stages is 25 stages. After we know the total number of trays, we need to determine inlet tray location. Using this formula, feed will be at tray number 13 from the top. Next, tray spacing is selected to be 0.45. An extra of 15% of total height is allocated for disengaging space and sump. With that, column height is determined to be 12.564 meter. Next, we need to calculate the column diameter using this formula. The calculated column diameter is 1.912, which makes our height to diameter ratio is 6.6, which is acceptable. So for liquid flow arrangement, double pass is selected as the liquid flow according to these properties. Next, for entrainment checks, it is calculated that our percent flooding is only 6%, which means that entrainment is unlikely to occur. For whipping point, the calculated minimum velocity of vapor is 5.243 meter per second to avoid whipping. So moving on, wear length is 1.453 meter while its height is 50 millimeter as recommended by CNOT. Next, number of holes with diameter of 5 millimeter is calculated to be 11,000 holes when 10% of active area is taken as the total hole area. Proceeding to process design number 12, plate pressure drop. Using the equation, pressure drop is calculated to be only 1.5 kPa, which is accepted. Last aspect for process design is downcomer backup. Its height is calculated to be 323 mm, which is less than tray spacing, hence it is accepted too. Moving forward to mechanical design section where material selection and its design pressure, temperature and stress are decided and calculated. Carbon steel is used as it is durable. For welded joint efficiency, 0.85 is chosen. Next, corrosion allowance is set to be 2 mm as recommended by CNOT. Mechanical design item number 4, shell thickness, is calculated to be 13 mm including corrosion allowance. For distillation column and closure design, torus spherical closure is selected as it is most economical for low operating conditions. The closure thickness is calculated to be 20.3 mm. Another point in mechanical design is design subject to combined loading, as column usually subjected to extra loads other than pressure. For distillation column located in Sungai Udang, Melaka, only weight and wind load will be considered. Thus, its weight load, or we call dead weight, is 163 kN, while wind load is 4,190 kN per meter length of column. Next is skirt design. Skirt design is equally as important because it provides support for vertical column like our distillation column. It is designed to be 3 meter high and 20 mm thick as it is satisfy these two decision criteria. Last but not least is the nozzle sizing for column inlet and outlets. The duct diameter for feed, bottom and distillate is calculated to be 500, 170 and 310 mm respectively, and all have 3 mm thickness. After design is accomplished, a specification sheet is created which contains the operating data, inlet-outlet conditions and technical data. With that, a technical drawing consists of column side elevation, tray plan view and tray side elevation has been drawn. Thank you for listening. Have a good day.
Assalamualaikum warahmatullahi wabarakatuh. I'm Aimal Aqilah binti Muhammad Hanif, and I'm from group 15. So for my presentation, it has two parts. The first part is the individual part, which contains the design methodology of furnace F101, the design screening process design of F101, technical drawing, and cost estimation for F101. The second part that I will be presenting is the group presentation, which is I'm going to be presenting the laws and regulations. For the design methodology, it involves design screening, which is it is important to determine the type of furnace to be used based on the inlet and outlet temperature of stream. And then the process design, the mechanical design, technical drawing, and equipment costing estimation. For the design screening, we reviewed several types of furnace, which are box furnace, cabin furnace, and cylindrical furnace. This classification is based on the amount of heat absorbed by the fluid to be warmed up. This depends on the type of solution. Normally for vertical cylinder type, it's adequate to operate up to 29.1 kilowatt, while cabin or box are for higher values. So as we see, our type of furnace is chosen based on the inlet and outlet stream, which is the cabin furnace. Next are the process design of furnace 101. To calculate all the important radiance and convective points, there are several assumptions that are to be made, which are the average radiant heat flux, and the heating medium, which is fuel gas, excess air, which is up to 20%, and the length of tube is 30 feet. So for calculation, the fuel consumption rate, according to the calculation, the fuel consumption rate is 37,360 pound per hour. So there are two sections, which are radiant section and convective section. For radiant section, the effective radiant transfer rate is calculated and it is equals to 148,000 British thermal unit per hour feet squared, and the radiant heat duty is calculated with the efficiency of 56%. The calculation of L of the length and diameter are as followed, and it's given by 61 feet and the diameter is 92.42 feet. The surface area is 25.45 feet squared. From the surface area, we can have the tube dimension, which are area of tube is 1.85 feet squared and number of tube is 58. As for the convection section, the efficiency of the convection section is 82% with the heat transfer of 131.03 BTU per hour feet squared Fahrenheit. The number of tubes are 27 with thickness of pipe 0.0215 inch. Given is the technical drawing of the radiant and convective section. For cost estimation, based on Sinot and Towler 2020, the given equation will give us the purchase equipment cost based on 2017, given the CE index 509.7. Using the appendix given, the equipment of choice is box furnace, and then the duty is calculated in megawatt. So computing all the values and we'll get and converting it to Malaysian ringgit, we will get 7,106,297 ringgit and 74 cents. For facilities that stores, releases, transports, treats, or disposes of scheduled waste are subjected to the following regulations, which are environmental clean air regulation, environmental quality scheduled waste regulation, environmental quality sewage, and industrial effluent regulation. So based on our waste, which is alumina, it is alumina and zeolite are under waste catalyst, while cobalt molybdenum is under sludges containing one or several metals. And for other waste, it is categorized under acidic sludge because it contains ammonia and several other chemicals that are